Hello and welcome. Let's continue with chapter 2. Let's start off with chemical bonds now. When we talk chemical bonds, I want you guys to know bonds are what hold atoms together when they combine. Now, when we talk bonds, bonds you'll see they're not physical structures. They themselves are not actual physical structures. They are just an energy relationship between the electrons of the reacting atoms. And they're going to be made and they're going to be broken, you'll see, in less than a trillionth of a second, these chemical bonds. So when we go through and we talk chemical bonds, they're energy relationships you can see between electrons of the reacting atoms, and the electrons can occupy up to 7 electron shells, energy levels around the nucleus. We'll see, we won't get into talking about all 7. That's something chemistry will really get into and focus on. Here we'll get into the third electron orbital, and we'll see how many electrons can be found occupying the first electron orbital, the electron shell, then the second one, and then the third one. And like I said, then chemistry will get into subshells when you talk about SPF and D, and it's been like. So here when we go through and we talk electrons, we're going to see now the electrons forming the electron cloud around the nucleus of an atom. They're going to be occupying regions of space called electron shells or electron orbitals. Okay? They always surround the nucleus of the atom. And we're going to go through and we're going to see, we're going to give these electrons in the outermost shell, whichever shell that may be of the three, a name. And we'll see, we'll refer to that shell as the valence shell, and the electrons will be the electrons in the valence shell. So we'll talk about that in a few seconds as well. Now the atoms, I told you, can have electrons in up to 7 shells, but the actual number of electron shells is going to depend on the number of electrons that that atom actually has. Each electron shell is going to have one or more orbital. So that's basically, you can think of as a seat for the electrons. Now I want you to also understand that each electron shell is going to represent a different energy level. So you need to think of electrons as particles with a certain amount of potential energy. Now we'll see later how they're going to use their energy then in producing ATP. So how much potential energy does an electron have, you may ask? Well, that answer is going to depend on the energy level. Okay, or you can say the electron shell. Now, the attraction between the positively charged nucleus and the negatively charged electrons is greatest when these electrons are closest to the nucleus. Okay, so again, this attraction between the positively charged nucleus, right? Because we're going to see the neutrons don't have a charge to them. So the positively charged nucleus, okay, and this attraction between the electrons is going to be greatest when the electrons are going to be closest to this nucleus. And then the further they move, okay, that attraction then starts to fall off. So the attraction starts to decrease with increasing distance from the nucleus. Okay, so I'm saying basically there, the closer the nucleus, the closer to the nucleus the electrons are, the greater attraction that they have for one another. The further the electrons are from the nucleus, the less amount of an attraction that they have. So basically what we're really saying there, when you go back and you are going to think about the big picture, is that the electrons that are going to be the furthest away are going to be the ones that are going to be reacting in the chemical bonds. That's what it comes down to. Okay? So here now, I want you to know again, now that statement that I just made, that statement explains now why electrons furthest from the nucleus, number one, have the greatest potential energy because they're able to react. The greatest potential energy. Attraction here, less with the nucleus. And number two, they are also the most likely to interact chemically with other atoms. They aren't tightly held by their own nucleus, and they are easily influenced by other atoms. Now, each electron shell can hold a certain number of electrons. Shell number one, which is the shell that's going to be immediately surrounding the nucleus. The shell immediately surrounding the nucleus is going to be able to hold only 2 electrons. It can hold only a maximum amount of 2 electrons. Shell number 2 then, the second shell, so let me actually show you a shell. So here we could see we've got the nucleus for helium, and then here we could see we have also the electron shell out here. So this is the first shell. This shell can hold a maximum of 2 electrons. A maximum of 2 electrons. Now shell number 2, so you can see here's a second shell that's drawn around. This one doesn't have it because it's only got 2 electrons. If it had more electrons, then we would have to draw in the next shell, and we'll talk about that as well. So shell number 2 then holds a maximum of 8 electrons. Holds a maximum of 8 electrons. That's what I'm kind of pointing to here. We're going to talk about the rule of 8, basically the octet rule. Shell 2 holds a maximum of 8 electrons. It's 2 plus 6, S, then P. So then electron shell number 3 then. 3 is going to have room for 18. Okay? 3 is going to have room for 18. Now, 2, then 6, then 10. It goes what? S, P, D, and F, I believe, after that. But we don't worry about any of that. We're not going into that. Okay? What we're going to do is we're going to go through and we're going to say, except for the first shell, okay, which is going to be full with 2 electrons, atoms interact and have 8 electrons in their valence shell. Okay, 8 electrons in their valence shell. That's how I want you to know it. Okay, shell 3 can have 18 electrons because it has subshells that can accommodate more electrons, but these shells are going to fill at 8. They fill at 8 because that's the number of electrons that can participate in bonding, and that's known as the octet rule. Okay, so 2, and then 8, and then you have 18 there, but it fills at 8 is how I want you to know it. That's it. Then I want you to know which electrons are involved in chemical bonding. In chemical bonding, we'll see the only electrons that are involved are those in the atom's outermost energy level. That are in the outermost energy levels. The inner electrons, they are most likely to be tightly held together by the nucleus as we described. Now, if the outermost energy levels of an atom is filled to capacity, that atom is said to be stable and unreactive. Just like us, they like stability. Okay, so if the outermost energy level of an atom is filled to capacity, the atom is said to be stable and it's unreactive. Now, on the other hand, if atoms are not filled to capacity, they tend to gain, lose, or share electrons. Or share electrons with other atoms to achieve stability or to become stable. Now, valence shell, the term you see there, is the term that indicates, we said, the atom's outermost energy level that is chemically reactive. That is chemically reactive. There are 3 major types of chemical bonds that we're going to visit. So let's go through and let's check out the types of chemical bonds. So again, there are 3 major types. Now these bonds, they result from attractive forces between atoms. They result from attractive forces between atoms. So chemically reactive elements are elements whose valence shell is not full. And what did we say? They're going to tend to gain, they tend to lose or share electrons with other atoms to achieve stability. Like us, they want stability in life too. So here we could see chemically inert elements. You can see Helium has 2 electrons. It doesn't tend to gain, lose, or share electrons. And here you can see 2, 4, 6, 8 in neon's valence shell. Chemically inert elements. See, their valence shell is complete. Here's some chemically reactive elements, though. Hydrogen, you know that. Carbon, okay, there's only 1 electron here, so it has the ability to gain or lose. Carbon, 1, 2, 3, 4. It can do that with 4 different atoms, 4 different hydrogen atoms even. Okay, or 2 and then form a double bond somewhere. But again, that's getting too detailed. Oxygen here is also reactive. Look at here, 2, 4, 5, 6 electrons. And then look at here, sodium. Sodium has only 1 electron in its valence shell. So we're going to go through, we're going to check all this stuff out. It's fun. Now the types of chemical bonds. Again, there's 3 major types. We have ionic, we're going to go through, we're going to check out ionic bonds. We're going to check out covalent bonds. And we're going to check out some hydrogen bonds. The weakest bonds, the little weaklings. They're more of an attraction, we'll see. They're not really true bonds. So when we talk ionic bonds, first type, let's talk ionic bonds. Now, we said before that atoms are electrically neutral, right? We said atoms are electrically neutral because they have the same amount of positive and negative charges. Ionic bonds are bonds where electrons can be transferred from one atom to another. And when this happens, that precise balance of positive and negative charges that we have, they're going to be lost. They're lost so that a charged particle is formed, and it's called an ion. An ion. And we'll see ions are basically electrolytes. They're charged particles. Okay, we'll see that in a few seconds. So again, let me reiterate that. Ions, okay, is what we're talking about. In order to have an ionic bond, we have to form ions. Okay, that's what we're getting to. Before we said atoms are electrically neutral. They have the same amount of positive and negative charges. Positive comes from the protons. Negative comes from the electrons. So that precise balance, okay, when we talk about and we discuss ions, that precise balance is not there. The reason why it's not there is because we said atoms tend to gain or lose electrons. Now, when atoms tend to gain or lose electrons, what charge are they losing? Or what charge are they gaining? A negative charge. So you got to remember that. Electrons have that negative charge. Okay? So atoms gain or lose electrons, and they become charged particles. That makes sense. Now, if you have an electrically neutral atom, right, and same amount of positive and negative charges, let's say it gains another negative charge. Or let's say it loses an electron, a negative charge. You see that precise balance is lost there. That's what we're talking here. So when we talk ions, ions are charged particles which are formed because electrically neutral atoms transferred electrons from one atom to another. Now, because of their charge, they can conduct electricity when dissolved in water. Consequently, the ionic forms of mineral elements are collectively called electrolytes. And we'll see they can conduct electricity. And that will be when we get into action potentials. When we talk action potentials, we'll see that there. So then let's talk ionic bonds, right? That's what we came here to discuss. Now, ionic bonds, when we go through, we discuss them. I want you to know an ionic bond is a chemical bond that forms between atoms when they transfer one or more electrons from one atom to another. These ions tend to stay close together because we'll see opposite charges attract. So you have two atoms, one loses and the other gains. So the one that loses is going to lose a negative charge. The one that gains a negative charge. Okay? So now they're not electrically neutral anymore, right? They're going to become opposite charges. One will be positive, one will have an overall negative net charge. One will have an overall positive net charge, one will have an overall negative net charge because one lost the electrons. So if it loses the negative charge, right, it's going to gain a net overall positive charge. The one that gains the electron, okay, so the one that loses the electron gets an overall positive charge. Okay, we're going to see that. I'm just doing this in the air right now, but you're going to actually see that with the picture. We're going to use sodium chloride as an example. Okay, so you'll see that there. Now I want you to know the atom that gains one or more electrons is the electron acceptor. The one that gains one or more electrons is going to be called the electron acceptor, right? Because it accepts electrons. It gets a negative charge. It gets a negative charge and is called an anion. And it will now be called an anion. You can see that here, the term anion. And it has a negative charge, we said. So the anion, okay, is the atom that gains one or more electrons. The one that gains one or more electrons is called the electron acceptor, we said. And it's going to acquire a net negative charge, right? Because before it was neutral, but now when it gains an electron, which is a negative charge, its overall net charge now is going to be negative. So that's why the anion is negatively charged. It's negatively charged. Then the atom that loses electrons. The atom that loses electrons is the electron donor. You could think of the electron donor. It becomes known as a cation. I thought of it as the donor cat. The cat likes to donate. I had a picture of a rich cat with a cane and a hat, and a nice a nice animal fur, jacket, and donating. I don't know, So you got to do what you got to do to remember. That's what it comes down to. So the atom that loses electrons is the electron donor, and it's going to acquire an overall net positive charge, right? Because it lost a negative, so now it has more positives than it has negatives, because before it had an equal, right, amount of positive and negative charges. But when it loses, right, it becomes overall positive charge. If it gains, it becomes overall net negative charge. So it acquires a net positive charge. Now, example of ionic bonding is the formation of table salt. Or sodium chloride, NaCl. So let's check out an example of ionic bonding. Now, when we look at this example, here's an example of ionic bonding, and this example is an example of the formation of salt or sodium chloride. Now, sodium, I want you to know, has an atomic number of 11. Sodium has an atomic number of 11. It only has one electron, as we can see here, in its valence shell, in its outermost shell. It would be difficult to fill sodium's valence shell with 7 electrons. Okay, so it just donates its electron to make things easier. Now, when the electron is lost, this shell number 2 we have here, shell number 2 becomes the outermost shell, the valence shell, and it is full, or it's stable. So the sodium gains stability and becomes a cation. It becomes a cation, as we see here. And it gains an overall positive charge we described cation to get. Now, on the other hand, chlorine has an atomic number of 17. has an atomic number of 17, and it needs only one electron to fill its valence shell. By accepting an electron, it becomes an anion, and it achieves stability. Now, ionic bonds are commonly formed between atoms with one or two valence shell electrons, and that includes the metallic elements such as sodium, calcium, and potassium, and atoms with 7 valence shell electrons, such as chlorine, fluorine, iodine. Okay, so ionic bonds are commonly formed between atoms with 1 or 2 valence shell electrons and atoms with 7 valence shell electrons. Now, when you talk about a difference in properties between a compound, right, we said compound is 2 or more elements that come together, and its constituent atoms, you see that sodium is a silvery white metal, and chlorine, I said, is a poisonous gas. But when the two come together, when they're combined, they form white crystalline solid that we're going to be sprinkling onto our food to elicit a greater taste. And we do it with higher quantities when we have a cold or we're sick because of our lack of ability to smell. Most ionic compounds are going to fall under the category called salts. They'll fall under the category called salts, and they exist not as individual molecules, but as crystals. Now, in order to achieve stability, electrons don't have to completely transfer electrons from one atom to another. No, they don't. They can also be shared so that each atom is able to fill its outer electron shell at least part of the time. And these bonds are said to be the second type of bond we'll talk about, which are covalent bonds. So we talk covalent bonds. Covalent bonds are bonds in which electrons are not completely transferred from one atom to another atom. Instead, they are shared. They are shared so that each atom can fill its only electron shell at least part of the time. Electron sharing produces molecules in which the shared electrons occupy a single orbital common to both atoms. Hydrogen has a single electron and can fill its only shell by sharing a pair of electrons. When it shares electrons with another hydrogen atom, a molecule called hydrogen gas is formed. The shared electron pair, it orbits around the molecule as a whole, satisfying the stability needs of both atoms. So here, with that hydrogen, or we don't have to draw it here, basically with these electrons, they're going to be radiating around this hydrogen and then around this hydrogen, around this hydrogen and this hydrogen, so helping to fill its valence shell part time, 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 and just basically keep rotating back and forth just like that. Hydrogen can also share electrons. Okay, hydrogen can also share an electron pair with different kinds of atoms to form a compound. Carbon has 4 electrons in its outermost shell, we saw. It has 4 electrons in its outermost shell, but again, it needs 8 to achieve stability. Okay, it needs 8 to achieve stability. So hydrogen has 1 electron, but it needs 2 electrons to achieve stability. So here you can see one carbon can share electrons with 4 hydrogens. So 4, 1, 2, 3, 4, because the hydrogens have 1 electron, and the carbon has 4 in its outermost shell. So the 4 and its 4 equal 8, and it achieves stability. And it forms, as you can see here, methane gas, methane molecule, CH4. You can see the structural formula, and here we have the molecular formula. And same thing here with our hydrogen gas electron model. You have the structural formula, and then we have the molecular formula. Now, carbon shares 4 pairs of electrons with hydrogen atoms. Again, the shared electrons orbit and belong to the whole molecule. Okay? Orbit and belong to the whole molecule, ensuring stability of both atoms. Now, when 1 pair of electrons is shared, as we see here, when 1 pair of electrons is shared, excuse me. Now, when 1 pair of electrons is being shared, okay, here we can see we have what we call a single covalent bond that's going to be formed. Same thing here. You have a single covalent bond being formed between this carbon and this hydrogen, between this carbon and this hydrogen. Same thing here between this carbon and this hydrogen. Same thing between this carbon and this hydrogen, and same thing down here also. So, single covalent bonds. Now, when 2 or 3 electron pairs are shared, then you have what we call double or triple covalent bonds. Double or triple covalent bonds. And here you can see we can identify a double bond between these 2 oxygens. Now here between these 2 oxygens, what we see here is 4 electrons, so 2 pairs of electrons being shared. Now when we talk about 2 pairs of electrons being shared, it's indicated by these 2 horizontal lines. So that's telling you there's a double bond here. Now if we talk triple bond we can see right inside of here between these 2 nitrogen atoms. Here you have then 3 electron pairs being shared, right? 6 electrons. So we have 3 lines that we'll use in the structural formula to depict that. So single bonds, single covalent bonds, double covalent bond, and then triple covalent bonds. Now, I want you to know during covalent bonds, the shared electrons are shared equally only most of the time. When they are shared equally, they give rise to nonpolar molecules. So when the electron pairs are being shared equally, they are going to give rise to nonpolar molecules. So during covalent bonds, the shared electrons are shared equally only most of the time. Now, when they are shared equally, they give rise to what we call nonpolar covalent molecules. Now, nonpolar molecules are electrically balanced molecules that are formed by covalent bonds. And one example will be carbon dioxide. Here we can see carbon dioxide is linear and symmetrical, and they are considered nonpolar molecules, where you have equal sharing of electrons taking place. Now, if the electrons are shared unequally, this creates polar molecules. Polar molecules. Dipole molecules, we can see there. Polar molecules are molecules in which you have unequal electron pair sharing taking place. It's unequal pair sharing because one atom attracts the electrons to its side, and this creates a charge, a net charge for that side then. Water is a polar molecule. Water is polar because the oxygen pulls the electrons to it. This gives a positive charge to the hydrogens and a negative charge to the oxygen, creating two poles of a charge. And you can see it's not a symmetrical linear model anymore. It's a V-shaped molecule now versus carbon dioxide. So water is considered polar. Next, then, let's move. Okay, so we'll move, and we can see then we have ionic bonds we talked about, polar covalent bonds, and then nonpolar covalent bonds. Next, then, let's talk about our third type, hydrogen bonds. Hydrogen bonds. Now, hydrogen bonds, they're not as strong as the ionic and covalent bonds as we described. Hydrogen bonds are really not true bonds. They're more like an attraction than a true bond. Hydrogen bonds form when a hydrogen atom that is already covalently linked to one electronegative atom is attracted by another electron-hungry atom so that a bridge forms between them. So hydrogen bonds form when a hydrogen atom that is already covalently linked to one electronegative atom is attracted by another electron-hungry atom so that a bridge forms between them. Hydrogen bonding is responsible for the tendency of water molecules to cling together, and also forms films, referred to as surface tension. And this explains why water beads up into spheres when it hits a hard surface, and why water striders, animals, as we see in this picture, can walk on a pond's surface. So you see here an already covalently linked molecule is attracted, you can see, by this other covalently linked molecule's atoms. And you can see here then, you can have a water drop, another water drop, another water drop, all coming together, forming a bigger drop of water. Some proteins and DNA have numerous hydrogen bonds between them as well. We're going to go through, we're going to check out, and we're going to see. Let's talk then chemical reactions. Chemical reactions occur whenever chemical bonds are formed, rearranged, or broken. Chemical equations, I want you to know about, are the symbolic ways of writing a chemical reaction. A chemical equation is like a sentence describing what happens in a reaction. A chemical equation will contain in it reactants, products, and the proportion of each reactant and product. So when we talk reactants, reactants are the number and kinds of reacting substances. Products are molecules formed from combining the reactants. And then third, we said the proportion of each reactant and product as well. The reactants are atoms as we can see from the atomic symbol. So here we can see one example of a chemical reaction and being indicated by a chemical equation. And we'll go through and we'll check that out. So again, the reactants are atoms as we can see from the atomic symbol. And the products are molecules and are represented by their molecular formula. Here we see the reactants are two hydrogen atoms. So when these two hydrogen atoms react, they form this product, hydrogen gas, H2. So the molecular formula, H2, we can see is representing the product. 4 hydrogens react with a carbon. So these are the reactants. Okay, so here's the chemical equation you see. It contains the reactants, the products, and then the quantity of each. So 4 hydrogens and a carbon are going to react, creating then CH4 or methane. Let's talk about the patterns of chemical reactions. Most chemical reactions exhibit one of 3 patterns. They're either going to be synthesis reactions, or decomposition reactions, or third, exchange reactions. Now, first, when we talk about synthesis or combination reactions, synthesis reactions always involve bond formation. They always involve bond formation. They are combination reactions. They are combination reactions where we can say A plus B is going to form AB. During synthesis reactions, atoms or molecules combine to form a larger or more complex molecules. So during synthesis reactions, atoms or molecules are going to combine to form a larger, more complex molecule. Synthesis reactions are the basis of constructive, or they're the basis of anabolic activities, such as joining amino acids together to make proteins. Here we can see exactly that. Here's a synthesis reaction. We're going to synthesize a protein molecule. How do you synthesize protein molecules? Right? We learned in like 7th grade, amino acids are the building blocks of proteins. So we get amino acids and we start putting them together. When we start putting amino acids together, we construct proteins. And this is an example of a synthesis reaction. Opposite, if we were to start breaking this protein down and form amino acids, that's an example of a decomposition reaction. Well, you're going to say, why would you do that? The digestive tract does that. That's how we get absorption to happen. You don't just absorb the hot dog, the steak, right? That's not what floats around in your bloodstream. It's its building blocks, which are going to be the amino acids. Now in decomposition reactions then. So in decomposition reactions, here, when a molecule is broken down into smaller molecules or its constituent atoms, we're able to appreciate the decomposition process then. So we had AB formed, we break it down, this is what it's going to form for us, A plus B. They are reverse synthesis reactions you can think of. They are the synthesis reaction in reverse. So they are reverse synthesis reactions, or you can think of them as degradative reactions, or you can think of them as catabolic reactions or processes. An example would be glycogen. Glycogen, you know, is a storage form of glucose, right, in our liver and muscles. When we break glycogen down, it forms for us glucose molecules. Here, bonds are broken, you see. Third type was exchange reactions, exchange or displacement reactions. These exchange or displacement reactions involve both synthesis and decomposition. Bonds here are made and broken. Bonds here are both made and broken. Here we can see an example of an exchange reaction. Here we're going to see ATP. This is basically one of the first steps of glycolysis you're going to be learning about. ATP gives up its phosphate to glucose. And glucose now becomes glucose 6-phosphate. Its maiden name was glucose. One way to think of it. Okay, so now it becomes glucose 6-phosphate. The reason why our body does that to glucose, so it can trap it inside the cell so it doesn't escape. Pretty crazy, pretty crazy. When all this stuff comes to life. So ATP then becomes ADP, adenosine diphosphate, no longer triphosphate, lost a phosphate. So an exchange reaction. So in these reactions, the reactant, okay, or I want you to, so they're going to be basically involving, we said here, both synthesis and decomposition. So bonds are both made and broken. Next up we have oxidation reduction reactions, or redox reactions. They're called redox reactions. They are decomposition reactions. They are the basis of all reactions in which food fuels are broken down for energy. In these reactions, the reactant losing the electrons is going to be referred to as the electron donor. And we say it's been oxidized. You have to know how to use those terms. The reactant taking up the electrons is called the electron acceptor, and it's called the electron acceptor, and it's said to become reduced. So you have to know how to use the term oxidized and reduced. So all three reactions, and then we saw the redox reactions. Next then, let's talk about factors influencing the rate of chemical reactions. So when chemical reactions occur, there's lots of different factors that can come in and influence the rate at which that chemical reaction is taking place. The first factor that I'd like you to know about here is going to be temperature. Temperature is one important factor. Increasing the temperature of a substance increases the kinetic energy of its particles. For this reason, the chemical reactions proceed more quickly at higher temperatures. Second factor is concentration. The higher the concentration of particles, the faster the reactions occur because more particles are around and collide with one another. As the concentration declines, the reaction slows. Third factor is particle size. Smaller particles move faster than larger ones and tend to collide more frequently and more forcefully. The smaller the particles, the faster a chemical reaction goes. And then last is a catalyst. Catalysts are substances that increase the rate of chemical reactions without themselves being chemically changed. So catalysts will enter the chemical reaction and they'll exit the chemical reaction without ever having been changed. All they'll do is speed up the chemical reaction and then they take off. Enzymes are biological catalysts, and we'll talk about them as we progress further throughout the semester. They're going to be very important for us. So you can see increasing the temperature increases the rate at which the chemical reaction is going to take place. Increasing the concentration of reactants increases the rate at which the chemical reactions take place. Decreasing the particle size increases the rate at which the chemical reaction occurs. And then adding a catalyst. Catalyst will increase the rate, again, without being chemically changed or ever being a part of the product.